Scientists built semiconductor clean rooms and ran 24-hour shifts across institutes to preserve Bennu's dust, calibrating advanced imaging and chemical analysis techniques to probe 4.5 billion-year-old grains. The moment researchers received the 121.6 grams of Bennu material, they knew they faced an unprecedented challenge. This wasn't just another rock sample. This was material that had traveled through space since the solar system's formation, and every precaution had to be taken to preserve its pristine condition. Research teams immediately began constructing specialized clean rooms with air filtration systems more advanced than those used in semiconductor manufacturing. The contamination protocols they developed went far beyond standard laboratory practices because even a single speck of Earth dust could compromise decades of scientific work. The analysis required instruments that pushed the boundaries of current technology. Each technique required months of calibration and testing before scientists could trust the results they were seeing. Teams worked around the clock in carefully coordinated shifts. While one group examined particles under electron microscopes, another team prepared samples for chemical analysis, and a third group processed data from the previous day's experiments. The 24-hour schedule was necessary because the instruments required constant monitoring and the volume of material demanded this intensive approach. Every single grain had to be cataloged, photographed, and analyzed multiple times to ensure accuracy. The data output was staggering. Each particle generated thousands of data points, and with thousands of particles to examine, the computational requirements quickly exceeded what standard laboratory computers could handle. Scientists had to develop new algorithms just to organize and process the information they were collecting. The pattern recognition software needed to identify mineral types, organic compounds, and unusual features required machine learning approaches that hadn't been used in planetary science before. Multiple research institutions coordinated their efforts through shared databases and regular video conferences. Teams at NASA's Johnson Space Center worked alongside researchers at universities across the United States, while international partners in Japan, Europe, and Australia contributed specialized expertise. The collaboration involved 200 scientists from 35 institutions across 6 continents, each bringing unique capabilities to the analysis. Some institutions specialized in organic compound identification. Others focused on mineral analysis, and still others contributed expertise in isotopic measurements. The first major findings emerged in late 2024, but these were just preliminary results. Scientists published papers showing that Bennu contained far more complex chemistry than anyone had predicted. The mineral diversity exceeded expectations. Organic compounds appeared in unexpected concentrations, and water signatures were found throughout the sample. These initial discoveries hinted that the full analysis would reveal even more surprising findings, but researchers knew they needed additional time to verify their results. The original timeline called for a 1-year intensive analysis period, but the complexity of the sample forced scientists to extend their work well into 2025. Every time researchers thought they understood a particular aspect of the sample, they discovered new features that required additional investigation. Mineral grains that appeared simple under initial examination revealed complex internal structures when viewed with higher resolution techniques. Organic compounds that seemed familiar turned out to have isotopic signatures that challenged existing theories about their formation. International coordination became crucial as the analysis progressed. Samples were carefully divided and shipped to specialized laboratories around the world, with each institution contributing their particular expertise. Japanese researchers used advanced ion beam techniques to examine individual mineral grains. European teams applied cutting-edge organic analysis methods developed for studying meteorites. Australian scientists contributed expertise in shock metamorphism analysis. American laboratories coordinated the overall effort and maintained the master database of results. Quality control procedures required multiple independent measurements of every significant finding. When one laboratory identified an unusual organic compound, at least 2 other institutions had to confirm the discovery using different analytical techniques. This redundancy was essential because the implications of the findings were so significant that scientific credibility demanded absolute certainty. The peer review process for the resulting papers was more rigorous than typical because the discoveries challenged existing models of asteroid formation and evolution. The computational challenges grew as more data accumulated. Scientists needed supercomputer time to model the complex chemical processes that had occurred on Bennu's parent body. The simulations required to understand how organic compounds could survive for billions of years pushed computational chemistry's limits. Researchers developed new software tools specifically for asteroid sample analysis, tools that will likely be used for future sample return missions. By early 2025, the coordinated effort began producing peer-reviewed publications that painted a comprehensive picture of Bennu's composition and history. The findings exceeded all expectations in terms of scientific value. Each paper revealed new aspects of asteroid chemistry, from the preservation of organic molecules to the complex history of water-rock interactions. The sample provided insights not just into Bennu itself, but into the broader processes that shaped the early solar system. The methodical approach finally yielded results that justified the extensive time and resources invested in the analysis. Scientists published definitive explanations for mysteries that had puzzled them since the sample's return. The success of this analysis marathon established new standards for sample return mission protocols. Future missions to asteroids, comets, and other small bodies will benefit from the techniques developed during the Bennu analysis. The 2025 conclusions represented more than just scientific discovery. They demonstrated that methodical, careful analysis of extraterrestrial samples can yield insights that reshape our understanding of planetary formation, asteroid evolution, and the distribution of organic compounds throughout the solar system. The 2-year effort established Bennu as the most thoroughly studied asteroid in history, providing a baseline for understanding similar objects that pose potential threats to Earth. Yet among all the discoveries that emerged from this intensive analysis, one particular finding had puzzled researchers from the very beginning: solving the black dust mystery. When scientists lifted the lid on the OSIRIS-REx sample canister that September day in 2023, they expected to see clean electronics and organized sample containers. Instead, they found themselves staring at a fine coating of black dust scattered across the avionics deck and clinging to metal surfaces throughout the canister. This wasn't supposed to happen. The sample had been sealed in a secure container during the entire journey from Bennu back to Earth. So where did this mysterious dust come from? The answer lay in the violent physics of the sample collection event itself. A nitrogen jet shockwave blew fine Bennu dust back into tiny crevices of the canister, explaining the black coating. When OSIRIS-1 released high-pressure nitrogen gas onto Bennu's surface during the touch-and-go sample acquisition mechanism operation, the blast created much more dramatic effects than mission planners had anticipated. The nitrogen jet hit the asteroid's surface with tremendous force, creating a shockwave that propagated across the surrounding terrain and pulverized surface materials into particles much smaller than the rock fragments the collection mechanism was designed to capture. To confirm the dust's origin, researchers immediately began spectral analysis of the particles. They used infrared spectroscopy to identify the chemical signatures of the material, comparing them to known Earth minerals and spacecraft components. The results ruled out terrestrial contamination completely. The dust showed none of the chemical markers typical of Earth materials, and it didn't match any of the metals or composites used in the OSIRIS-REx spacecraft construction. Advanced chemical analysis techniques determined the exact composition of individual dust particles. Mass spectrometry broke down the particles into their constituent elements, while X-ray diffraction revealed their crystal structures. These tests produced a startling result. The dust contained identical isotopic signatures to the main Bennu sample. The ratios of different isotopes of carbon, nitrogen, and oxygen matched perfectly with the larger rock fragments collected from the asteroid's surface. The breakthrough came when researchers modeled the physics of the nitrogen gas blast in detail. The force was so intense that it broke down larger particles into microscopic dust, creating a cloud of fine material around the spacecraft. The pulverization process was more extensive than computer models had predicted because Bennu's surface turned out to be much looser and more fragile than scientists expected. The shock wave created during sample collection was powerful enough to affect surface materials across a much wider area than originally anticipated. Some of the pulverized particles found their way into the sample canister through gaps in the sealing mechanism that were too small to be detected before launch. These microscopic openings were within acceptable tolerances for the mission, but they provided pathways for the finest dust particles to enter the canister during the brief contact period. The violent disruption of Bennu's surface during the nitrogen blast created conditions that allowed these tiny particles to infiltrate areas of the spacecraft that mission planners thought were completely sealed. When scientists analyzed the composition of the dust particles in detail, they made another significant discovery. The dust came from Bennu's most ancient surface layers, representing material that had been exposed to space for millions of years. This meant the dust was potentially more scientifically valuable than some of the larger rock fragments in the main sample. The surface layers contained information about how cosmic radiation and micrometeorite impacts had affected Bennu over geological time. The dust particles also showed higher concentrations of certain minerals compared to the bulk sample. Olivine and pyroxene, two important silicate minerals, appeared in greater abundance in the dust than in the larger fragments. This difference suggested that the asteroid's surface had been sorted by size over time, with smaller particles of certain minerals accumulating in the uppermost layers while larger fragments of different compositions remained buried deeper. Advanced imaging techniques revealed that individual dust particles contained multiple mineral phases mixed together in complex patterns. Some particles showed evidence of thermal processing that occurred when Bennu's parent body was still hot, while others preserved signatures of cold formation processes in the outer solar system. This mixing indicated that Bennu's surface represented a complex blend of materials from different parts of its parent asteroid. The solution to the black dust mystery emerged through 2025 analysis that combined all these findings into a comprehensive explanation. The dust represented some of the most pristine material from Bennu's surface, material that had been pulverized by the spacecraft's nitrogen gas blast and transported into the canister through microscopic gaps in the sealing mechanism. Far from being contamination or an unwanted byproduct, the dust turned out to be an additional scientific treasure. The discovery changed how scientists viewed the sample collection process. The dust provided information about Bennu's surface composition that complemented the larger fragments in unexpected ways. It offered insights into space weathering processes, surface sorting mechanisms, and the preservation of ancient materials on asteroid surfaces. The mystery that initially puzzled researchers had transformed into a valuable source of scientific data. The black dust mystery's resolution also influenced planning for future sample return missions. Engineers now understand that shockwave effects during sample collection can transport fine particles in ways that weren't previously considered. Future spacecraft designs will need to account for these phenomena, either by preventing dust accumulation or by designing systems to capture and study it systematically. The dust analysis demonstrated that even unexpected discoveries can yield important scientific insights. What began as a puzzling contamination concern ended up providing researchers with additional windows into Bennu's composition and history. The 2025 findings showed that the mysterious black dust represented some of the most ancient and scientifically valuable material collected from the asteroid's surface.